Hello everyone, this is Kaveh with lesson 8 of our common Lisp lessons with some OpenGL thrown in for fun, coming to you from Honolulu. And today we're going to talk about colors and applying them to groups and how we spread the colors amongst the elements of groups. Before we get to the meat of the lesson, I wanted to basically mention a couple of other things about OpenGL, no, excuse me, not OpenGL, Common Lisp and the philosophy of it. So I've come across these two functions recently, update instance for redefined class and ensure generic function. And I have mentioned previously, I think, in these series that Common Lisp was designed so that the sum of the language and environment is more than the sum of its parts. I should say the totality of the language and environment is more than the sum of its parts. And part of this was done by taking into account not just the language spec itself, but also the environment in which it's run and the use cases in which users put it, especially the philosophy of working in a live image and updating it as you go along. So these two functions were examples of functions that were included so that you can basically do the things that we've been doing up to date. So this one here, update instance for redefined class, is something that gets called behind the scenes when you redefine your class in a live image, and you can carry on working because all your instances have been updated. I think technically they actually get updated when they get accessed, not when you redefine the class. An ensure generic function does a similar thing when you want to make a regular function into a generic function and then write methods for it. It does the same thing and allows you to do that and carry on working and not have to exit your image and recompile and relink and then go back into your environment with all the new definitions. So that was just a little bit of a side. Last time we defined a couple of functions, set fill color and set outline color, which did the appropriate things for groups and traversed all the nodes of a group down the hierarchy and set the colors for us. And we were a little bit clever so that it could basically take a color or a function that it would then evaluate to extract the color. So if we wanted to define something, for example, called randomized colors using that set fill color, we simply give it the crand, which generates a random color for us. So let's define that. And then we'll also do a similar thing here where we give it two colors and it'll generate a random color in between those two colors for us, and then we wrap that into a lambda and pass that to set fill color as well. Now let's make a grid of squares. So this will be a little useful function for us. So it basically makes a square shape of a given size, and then takes the grid points method that we defined, function that we defined earlier, and creates an n by n grid of squares in there, and then uses a scatter group function that we defined that takes a lambda that creates a shape and a list of points, and instantiates that shape along those points. So if we now define a grid of points, here we have it. And so this is a 14 by 14 grid of points that we've defined. And let's, for example, set the background of our scene to be gray. My machine is being slow today. I think I have too many processes running. The CPU is kind of going nuts, as I can see. Not sure why. Pardon that interruption. I just exited some stuff to make the CPU a little bit less strained. So we have our shapes, our grid of shapes, and we can set the outline colors to be black. And then we can use the randomized colors that we just wrote up here to assign each of the squares a different color, random color. And then we can set the outline colors to be 0, but also with a 0 alpha. So in other words, it'll be 100% transparent, i.e. no outlines. So we just have that now. And if we randomize the colors within a given range between black and blue, with an alpha of 0.25, we get sort of a mostly transparent shapes between black and blue. And if we set them with no alpha, so alpha defaults to 1, so that's 100% opaque. This is basically random colors between black and blue. So basically just different shades of blue. Now, just for fun, we're going to write a little function here called randomize group points. And what it does is basically traverses the hierarchy, and for each shape, it randomizes the points of the shape by a certain delta. So you can see the points on the vertices of the shapes move a little bit each time we do this, and we get different shapes. Now we'll try this process again with a new function that we call make random squares, that basically does the same thing and scatters the shapes, the squares, but along a group of random points instead of being in a grid. And so here we have a bunch of overlapping randomly placed squares. So let's go back up and kind of run through our little process again, just for fun. So let's set the outline colors to black. Let's randomize the colors of the shapes. Let's leave the outline colors there. We don't have to make them transparent. And then if we go between black and blue, again with a very lowish alpha of 0.25. Now if we want to make this like really very transparent, so this is very, very transparent shapes with an alpha of just 0.05, which is quite low. Let's undo that. And then if we make the alpha opaque again, we just get these shapes between black and blue. I need to have some coffee, even if it is decaf. I feel I'm mumbling a lot today and not making coherent sentences. There we go. Let's see if that helps any. And then if we randomize the points on these now, it's a little hard to see what's going on. So let's set our outline color to be white. Oops, close the parenthesis. There we go. Just reset it so I don't forget for later. But now if we randomize the points, maybe by a slightly larger amount, you can see what it's doing. Now, one of the things we might want to do is vary the existing colors of our shape by color delta. And this is not something we can do with set fill color, because set fill color just takes a color value or a function and assigns it to the color. Here we want to basically jitter the color, the existing fill color of the appearance, by a C delta. So we use our old-fashioned do hierarchy, which is what we built our set fill color on. And we can also have a set group alpha, which does the same thing, which goes through and just sets the alpha value of the color. But we can't do that again with set fill color because it sets the entire color with an alpha option. So if we set the alpha of all our shapes to be quite low now, you can see they're mostly transparent. And if we jitter the colors, you can see they vary slightly as we go along. And then if we do a set fill color, we can set the colors to be a greenish color and then go back to jittering the colors. And we can see that the greens vary slightly as we go along. hopefully YouTube's compression is not going to kill that. We can actually see what we're doing. So what we really want to do now is we want to basically be able to modify a color and set a color as alpha and modify color as alpha and do all these things in one function that's more general than set fill color. So for that, we define a couple of helper functions. The first one we call cadd, which destructively modifies the color by adding another color to it, and whether it may or may not affect the alpha based on the key flag here that we give it. And then we have another function that just sets the alpha of the color destructively, and one that adds to the alpha destructively. So now that we have these basic functions defined, what we're going to do is we're going to write a very general set shape color function. And this is basically going to take, just like set fill color and set outline color, a value or a function, but then it's going to take a number of flags. And these flags are defined here in the methods. So it takes a component flag that can be RGB keyword, alpha keyword, or RGBA keyword. And it determines what parts of the color are going to be set. And then there's a part, what components of the color, are going to be set. And then we have a part flag, which is either fill or outline, which determines which part of the appearance is going to be set, whether it's the fill color of the appearance or the outline color of the appearance. And then we have an operation, which is either you set the color or you add and modify the existing color. So first thing we do is we define a method for the case where there is no type. It's the most general type. It's basically the method that gets called if no other more specialized methods are encountered. And we just do nothing. We just declare, ignore the value, ignore these parameters, and just do nothing. Then the meat of the function is in this method here where you give it an appearance. It counters an appearance. And then what it does is basically it computes the value that we're trying to set it. If it's a function, it does the func call of the value or function and returns the value, or it just takes a value by itself. Now, the thing to keep in mind is the value doesn't have to be a color. The value can also be an alpha. And because of common Lisp dynamic typing, we don't have to specify a type, return type for value or function. So value or function can be either a function, a color, or an alpha value, and this will work. So, and this is a color that we're going to be affecting in the appearance. So if it's the part is fill, we take the fill color. If the part is not fill, we assume it's outline, we take the outline color. And then this is the color that's going to be destructively modified. So if the component is alpha, then if it's a set operation, we basically set, if the component is not alpha, if the component is RGBA, which means that all the components of the color, and the operation is a set, then we call a destructive cset function with the color and the value, and we give it the alpha flag to be true, in other words, modify the alpha as well. And if the operation is not set, we assume it's add, and then we just add the color to the existing color. If the component's RGB, we do the exact same thing, except we pass an alpha flag of nil, because we don't want to modify the existing alpha of color. And then if the component is alpha, it's the same thing again, except that we call cset alpha and cadd alpha to the color, and value in this case we know is going to be a floating number and not an array color. And then similarly to set fill color, we pass this down. So basically, as we encounter shapes in our hierarchy, if it's a polygon shape, we apply the same method onto its appearance, which then calls this method up here and does the actual setting of the color and the appearance. And if we're encountering groups, we just basically do nothing for the group itself, because groups don't have appearances, and we loop through all the children and set shape color onto the children. And if the children are polygon shapes, this gets called, and then this calls appearance. So we've defined this big generic function now. So now what we do is we redefine our functions randomized color, range, in terms of set shape color. And for these guys, it looks quite the same. There's no big difference. But now, since we have these flags component operation, we can jitter color shape color as well by defining jitter shape color. And what it does is it uses the operation flag, sets the operation flag to be add. And then that will add the RGB color to the existing color of the appearances. Same thing with set shape alpha, which simply uses the component alpha setting and just sets the alpha and doesn't modify the rest of the flag. So let's test that out a little bit. Let's make our hex shape that we like. And for fun, let's randomize the points a little bit so it's not so regular. So something like this, perhaps, a little wobbly. And I'm also going to randomize the size of the shapes. So randomized group points just modifies the points. The transforms haven't changed at all. But I'm going to actually scale it up and down a little bit to give it something a little bit more random looking with different, some large polygons, some small polygons. So we set everything black. That's what we get. This is all now using our new set shape color function and the functions that we built on top of that. Randomize the colors. So we take the outline part and set the alpha to be 0 so the outlines disappear. And now we randomize the colors again between black and blue. We get this. And then we set the alpha component of our shape to be 0.25, so it's pretty low. If we set it back to 1, it becomes opaque again. And if we set the alphas to be white with a slight 50% transparency, we have 50% transparent border that's kind of white, appears a little bit grayish. And if we make them be transparent green, we get this shape, this color, this shape, pattern of colors. And then we can jitter the shape colors by a certain amount. So each time I call this, it jitters the shapes, the colors. And as you can see, if I do it more and more, the colors vary more and more because this is a cumulative change that's happening. Let's do a couple of more things. We'll take this other shape as well, which is kind of our wobbly cross. And let's run through the same kind of process with it, again, just for illustration purposes. So let's leave the points the way they are and just modify the transforms, scales a little bit, so the scales are all different. We can make them black, randomize the colors, make the outlines be, have an alpha of 0, make it vary between black and blue, make it transparent, 0.25, make them opaque again, 50% transparent white back borders, outlines I should say, and then the green, and then again varying the greens so we get different colors. Let's do a couple more things with transparencies and groups and so on. So we define a function called makeCloud group. Excuse me, let me grab a sip of coffee. And what this does is basically does a scatter group onto a bunch of random points. But then if we have a scale factor that we give it, it scales the shapes by their distance from the center of the cloud. So let's just basically make 100 circles inside this volume with a maximum alpha of 0.5, so they're mostly going to be transparent. And we're not going to scale it. So we basically have a rectangular area, and what's happening is the further away the shapes are from the center, the more transparent they are. So we interpolate the alpha here, and then we optionally interpolate the scale as well. But we're not doing the scale here, we're just doing the alpha. If we turn on the scale factor here, it's going to be a similar shape, except they've been scaled down, and I've changed the alpha. Let me reset the alpha back to 0.5. So if we compare these two, the difference is in this case, the shapes, the circles are not being scaled at all. This is the exact same thing, but the further away the circles are from the center, the smaller they are in scale. And if we then exaggerate this, instead of 100 circles, we put 1,000 circles and give it a maximum alpha of 0.05, which is pretty low. We start getting some interesting cloud-looking shapes that look like smoke or cloud or things of that nature. And if we assign these some random blue colors between blue and white, we get kind of different shades of blue. And it looks kind of artistic and interesting. If we want to kind of crank it up a little bit, let's do 10,000 circles. And that probably just kind of like overloads it and everything just appears opaque at that point because you have 10,000 circles that are overlapping. But this is kind of the shape that we get. And just some interesting values. And if we want to just randomize the colors of the shape completely, we get something like this. So this is what the underlying geometry actually looks like. All right, so that's lesson 8, and thank you for listening, and we'll see you soon. Bye.